Okay, the recording's going. Okay, so new section for today. We're starting in... And the screen. How long has the screen been off? Just seconds? Did anyone notice?
It's been off for a while.
It's been off for a while. Oh, I forgot to... I turned it off. Of course it's off. Okay, sorry. I spaced. It'll take a second for... Oh, that was quick. Okay, cool. Here we are. So, new section for today. I'm going to talk about cross products. Thing about cross products is they relate very strongly to some other ideas. And so that we can be fully prepared when we get to cross products, I'm actually going to talk about those other ideas first. And we're going to talk about this thing called geometric order of a list. That's what I'm calling it. And then also determinants. And I think a lot of y'all, hopefully, presumably, have seen at least some things about determinant in Math 218, possibly also previously, maybe in high school, who knows what. We're going to do this stuff first, and then we'll get to cross products after. Real quick, though, I will point out, you've heard me say this a bunch of times already, I have to make tough choices about what I spend class time on, and even about what I include as part of the course. So some of what is in my notes here on this, in this section 1.4 is not only are we going to not spend class time on it, but you're not responsible for it. And I'll be clear as we go through and get to those specific things. And mostly what it's going to be is the proofs. And I want to point out that even though you're not responsible for those proofs, there's a lot of neat ideas, possibly some aha moments that are in the proofs themselves. And so I do encourage you to look at them, but that's just an encouragement. And again, you're not responsible for the specific proofs that I will point out as we go along. Okay, so let's get into it. Geometric order of a list. So let's talk about 2 dimensions first. So we're going to start off in the XY plane, let's say. We're going to look at 2 vectors in the XY plane, but now very specifically, not just a pair of vectors, but an ordered list. You might say an ordered pair, but I'm going to say an ordered list of 2 vectors. So the order is important. In fact, ultimately, it is the way I have them ordered that is what I'm going to want to talk about. The ordering itself is what we want to describe. Okay, so let's talk about this ordering here where I have A, comma, B, by which I mean that A is first and that B here is second. So how would I describe this order? Now, of course, you could say, well, it's alphabetical order. Obviously silly. It's got nothing to do with geometry, right? So I want to know geometrically, what can I say about that order? Now, in order to talk about that, I have to actually see the vectors. So let's suppose that the vectors look like this. Specifically, A, let's say, is that vector. Keep in mind, A is first. Right? And then suppose B is this vector, let's say, and again, keep in mind B is second. So looking at this picture here, we have first there, second here. So first here, then here. You can even watch my finger. It's there, and then it goes to there. My finger moves what you might call counterclockwise. Anybody see what I mean? If this is first and that's second, getting from first to second is moving counterclockwise. So we would say, if these are the vectors in question, then this list, this ordered list, again, the order being important, A first, B second, this ordered list is a counterclockwise list. Okay. All right. Now here's the thing. There are other vectors, right? I mean, there's nothing, I'm not saying that, the vector A shall always be pointing that way, right? I mean, we could have A might be pointing that way at some point. Maybe B is pointing this way. And again, keep in mind, looking at this list, ordered list. A is first. So that's the first one. That's the second one. And then going from first to second. First to second. That is clockwise in this case. So so this is getting at the geometry of the list, you see. And so depending on how your vectors are arranged and depending on what order you write them down in, that list is either clockwise or counterclockwise, and that's what I'm going to call geometrically natural. Okay, and there's some neat natural properties that we're going to write down in just a moment. I do want to recognize, though, sometimes neither. Sometimes you have a list of vectors, like let's suppose it's these here, and it's just neither counterclockwise nor clockwise. It's just, in this case, they're the same direction, so there's no turning at all. You could imagine also, what if one of the vectors were the zero vector? Then it's just that's neither clockwise nor counterclockwise. You'll further notice that all of the cases where you just can't say clockwise or counterclockwise, they're all cases where the pair of vectors is dependent. So I'm going to lump that third category, all the versions of that third category, zero, not zero, parallel, whatever the case may be, dependent. Okay, now, most of the time, though, in some sense, clockwise or counterclockwise. Now, here are some features of clockwise and counterclockwise. Notice that if you have a counterclockwise list, again, keep in mind A first, B second. There you go, counterclockwise. If you look at the mirror images, you reflect over some line. Just imagine taking these vectors and just do them like this. Just reflect over that line. Flip it over that line. Notice that the reflections, again, keep in mind, A prime first, B prime second, clockwise. So the way I'll phrase this is I'll say clockwise and counterclockwise are mirror images of each other, because when you reflect a list that's one, the action of reflecting it turns the reflected list into the other. So, mirror images. Yeah, for your consideration. Here's another property. If you take the vectors on your list and actually change where they are on the list. So if you trade the positions of two of the vectors on the list, such as I've done there. See, I traded A is now where B was, and B is now where A was. Right? If you do that, that will change the order. So counterclockwise turns into clockwise. And you can see, again, that actually happening. This list over here, counterclockwise, same vectors with the order of the list changed, same vectors though, BA, now clockwise. Okay. Now these are, I don't think there's any tough cells here geometrically, right? This is all pretty believable. Last observation, this is again highly believable. It's just a matter of sort of thinking it through. If you have a list of vectors, A, B, if that list is counterclockwise, and if you then take all of the vectors, and both of the vectors in that list, you take them all and you rotate them all the same amount. So you do a rotation, all the vectors rotating by the same amount. The result is going to be another list that will also be counterclockwise. So rotations preserve order, you might say. If you rotate the whole picture, well then, in some sense, nothing happens, right? And so the metaphor I like for this is if you're looking at a clock and you watch the second hand's going clockwise, of course, right? You turn your head to the side, it's still going clockwise, right? Same thing, nothing happened. Okay, all right. Where it gets challenging, interesting, is if you ask, what's the three-dimensional version of this, right? Now, clockwise, counterclockwise, you all have seen clock faces since you were in, kindergarten, right? It's old news. What is a three-dimensional version of this? If we're in 3 dimensions, and if we have 3 vectors, and again, not just a set of 3 vectors, but an ordered list of 3 vectors. Like that. I've never seen a 3-dimensional clock. I don't know how to say clockwise, counterclockwise. That's not an option. What do you do? I want to be able to talk about, I want to be able to give a name to the geometric, something fundamentally geometric about this order itself. Not the 3 vectors as a set, but the order that I have them written down. What's the analog of clockwise, counterclockwise? So, this is a hand gesture, so I'm going to have to just literally wave my hands a little bit here. I'm going to start off by looking at, suppose we're looking at this case. We've got these 3 vectors, A, B, C. And we're looking at this list, A first, B second, C third. The following is an arbitrary convention. So arbitrary means that there's nothing magic about this, and somebody made it up and pulled it out of thin air. Convention means that planet Earth has agreed right, that this is how we're going to do it, and so we, in some sense, have to do it this way because everybody's agreed this is just how we're going to do business. So here's the deal. We're going to use your right hand. You're going to start with the index finger of your right hand. Your index finger points the way like if you're, something like that, with your index finger parallel to your palm. That's the first rule. Index finger pointing parallel to the palm. Your middle finger is allowed to bend, but I'm going to say the direction that it wants to bend. So, yes, I know you're physically capable of doing this. Let's not. Right? So the ways, you're only allowed to bend, again, arbitrary rules, only allowed to bend that middle finger the way that it wants to bend. Now, with that said, index finger first, middle finger second. Arrange your hand. You've got a lot of freedom on how you do your hand, right? Arrange your hand in such a way that the first finger points in the direction of the first vector. A is first. Point your index finger in the direction of A. B is second. Point your middle finger in the direction of B. And you can see I'm approximately doing that here, right, for that first arrangement of vectors. Index finger first, middle finger second. Okay. Now, having done that, notice that those 2 vectors define a plane. There's a plane here, defined by A and B. The thumb of your right hand will naturally, and again, don't know hand yoga, right? Your thumb it'll kind of naturally point on one side of that plane. If the third vector points on the same side of the plane that your thumb does, then we call this a right-handed list because it satisfies that rule. All right, now, does that make sense to everybody? Now let's look at the next little arrangement here. You see I have this labeled as a left-handed list. We'll come to that in a minute. But first of all, let's test. We know this is not going to work, but let's see how it fails. Let's try to see if we can arrange for this to be a right-handed list. Again, A first, B second, C third. Well, I can point my index finger in the direction of that A vector. See? There you go. Okay, now can I get my middle finger to go in the direction of the B vector? Remember, I'm not allowed to do this, but I am allowed to arrange my hand kind of however I want. I'm still pointing my index finger in the direction of the first vector. Now look at my middle finger bending the way middle fingers want to bend, and I've got my index finger in the direction of the second vector B. A first, B second. But notice now my thumb pointing. Now my thumb is pointing below that plane. Thumb pointing below, this third vector C here pointing above. And so you see this arrangement of vectors does not have this feature of right-handedness. But it's no problem with the left hand. Everybody see that? So, this is a right-handed arrangement of this list of vectors. This is left-handed. And then I think you can probably persuade yourself there are various different versions of when neither right hand nor left hand is going to work. And maybe these two vectors are parallel. Maybe this is the sum of those two. Maybe one of the vectors is 0. Maybe two of the vectors are 0. Whatever. There's various different versions where neither one of these works. They're all linearly dependent. And so that's the sort of the third kind of annoying, in some sense rare exceptions. I'm going to lump them all into one category, dependent. Okay, how do y'all feel about these things here? Does that look good? Seems kind of a weird choice, but it is geometric. Got to give me that. Right? And here's the really surprising thing about it. I claim that right-handed, left-handed in 3 dimensions, highly analogous to clockwise, counterclockwise in 2 dimensions. Let's remind ourselves, clockwise, counterclockwise, they're mirror images of each other. If you trade 2 of the vectors, it changes the order. And rotating everything doesn't do anything. Well, check it out. If you have, if you're looking at right-handed, left-handed in 3 dimensions, they're mirror images of each other. Trading 2 of the vectors changes the order, and rotations don't do anything. They have this right-handed, left-handed have all the same properties that clockwise, counterclockwise do. It's just that it's for 3 vectors in 3 dimensions instead of 2 vectors in 2 dimensions. And so I like to say that this is an analog. This is a 3-dimensional analog of clockwise, counterclockwise. Yeah.
Does it not matter which of the 3, like which 2?
Oh, yeah. Great question. I'm going to get to that. I am going to go a little bit more slowly through these. I just wanted to very quickly hit the highlights on all 3 of them. But yeah, let me go through the details now. I think this first one is a pretty easy pitch. Mirror images in the sense that if you reflect. I mean, the easiest way to see this is that, here you go, right? Right hands and left hands are mirror images of each other. It's just visual inspection, right? Is that satisfying? Okay. So let's look now at trading positions of 2 of the vectors. To answer your question, any 2 of the vectors. So what I've got here in this example is I'm trading the positions of A and B. And you see that A and B, A first, B second, turns into B first, A second. But I could have done B and C. I could have done A and C. Whatever. Any 2 of them. And I claim that this is going to change the order. You can see in this case it does. Left hand or right hand goes to left hand. Let's see, let me demonstrate that it started off right-handed, ended up left-handed. A, B, C, A first, B second, C third. Boom, right-handed. Right. These vectors, A first, B second, C third. Right-handed. But now let's look at this list. I claim that this list, BAC, is left-handed because B first, A second, C third. So it's right-handed. Excuse me. This ABC is right-handed. This BAC is left-handed. Yes.
Does anything happen when you trade 3, like the position of 3?
Great question. I am going to get to that in a minute. I'll give you a quick preview, and that is that when you have 3 things, there's a very short list of ways that you can rearrange 3 things, right? If you were to trade the positions of all 3 of them, in fact, what you've actually done is you've traded 2 of the vectors, and then you've traded a different 2 of the vectors. So what that is actually changing the order, followed by changing the order again. So it will go from right to left and back to right. And we'll see that in another point of view in a second here. Okay. All right. So again, lastly, it's independent of rotations. I think this is a pretty easy pitch. Here we've got, here you go, ABC, right-hand order, right? Now, to get to what I've got there, this looks, yeah, okay, right. So this is those vectors, right? So 1, 2, 3. If I rotate, it's still my right hand. Right? So I've rotated all of it. You can rotate your right hand around and it remains a right hand. You cannot rotate a right hand around and, oh my gosh, I got a left hand all of a sudden, right? It just doesn't work like that. So right hand, stay right hand. So rotations don't do anything. Okay. Okay, how are we doing? All right. Okay, so weird stuff. Yeah, there is a fourth property. There is no sort of two-dimensional analog of this. So this is like a new additional property. And this gets to what you were asking a second ago about changing all three of them. It's called cycling. And let me be explicit. Oh, my glasses. Cycling, for example, if you were to take the third vector and put it in the second place, take the second vector and put it in the first place, take the first vector, which falls off the end, and put it back over at the other end there. So this is called cycling. And it preserves the order. So the hand-waving demonstration I'll make of this is there's ABC, A first, B second, C third. Let's see here, can I do this? There's BCA. So ABC, BCA. Everybody see what happened there? Okay, so cycling, still my right hand, right? Cycling preserves the order. Okay. Alrighty. Let's talk about determinants. So now again, I think y'all have seen determinant before. Y'all have seen a bunch of algebraic properties of determinant and how it relates to systems of equations and such, right? I'm going to give you here a very geometric interpretation of the determinant. I think in an ideal world, you would have seen this in 218. You might not have, though, or if you did, you might have forgotten. So I'm going to make sure to say this. I think this is a really important fact for multivariable calculus. So it starts with a list. Again, an ordered list. We're going to start in 2 dimensions, so 2 vectors in R2. Ordered list, A first, B second. And from this list, I'm going to make various things. From this list, first I'm going to make a matrix. First vector, first column. Second vector, second column. So given the list, that determines a matrix. Now reminder, a matrix represents a linear transformation. So now I've got a function from R2 to R2. And now here's another, I guess, I don't know if reminder is the right word here, but observation. If you were to look at the unit square, S, and if you were to ask, okay, what happens when I take the points on this unit square and I put them into this linear transformation, what's going to come out? And I appeal to your sense of what linear transformations are. What comes out is going to be a parallelogram. And specifically, something very natural that you can say about this parallelogram, we know what the edge vectors are as follows. Don't forget that the colors. I have to think about the color. We'll use blue here. That's fine. So let's ask, what is the image of E1? There's E1, the sort of the first edge, if you will, of the unit square. The image of E1. Well, don't forget, images of standard basis vectors are columns. And so the image of E1 is going to be that first column. It's going to be that first vector. It is A. So yeah, the image is a parallelogram, but specifically it's a parallelogram where one of the edges of the parallelogram is A. And then analogously, if I were to look at the second standard basis vector, look at its image. Again, images of standard basis vectors are columns. Second column means it's the second vector on the list. That's B. Okay, now, here's the thing. I haven't really done anything yet. I've made a bunch of stuff, but I haven't asserted any, to speak of, any shocking facts. I've just observed that if you have a list of vectors, you can make a matrix, you can make a transformation, you can make a parallelogram. So what? So here's where I'm going to make my first substantial statement here, and that is this. Let's see here. The area of that parallelogram. The area of that parallelogram is equal to the determinant of this matrix absolute value. That is a substantial step. That is really not obvious. It's very far from obvious. Shocking, even, if you really think about it. Because, if someone were to ask you, imagine this is a high school geometry class, here, compute the area of that parallelogram there. Then you'd be thinking, okay, well, I'll drop a perpendicular right there. And, oh man, how am I going to compute the length of that Well, okay, I could take the length of this edge. That's a magnitude. That involves square roots. So I could take the length of that edge and I could look at this angle. How am I going to compute that angle in the first place? But I guess I could compute that angle, and then I would take the sine of that angle and multiply by this length, which is the square root, and then multiply all of that by this length, which is the square root. And you've got square roots and trig and hard calculation. And my claim that I'm making, that I claim is a shocking fact, is that, or three-function arithmetic. Right? All of that trig and square roots and stuff, no, you could just compute this determinant. Three-function arithmetic, don't forget to take the absolute value. Boom. Really, really surprising, shocking fact. Let me just pause there for a moment. Does everybody see how that's kind of an eyebrow raiser? Any questions? I'm not going to prove this fact, by the way. There's several ways I know to prove this fact. The best way that I know to prove this fact that uses techniques that we conveniently have at our disposal is long and tedious. The best way that I know how to prove this in general involves techniques that we don't have at our disposal. So I don't want to do the long and tedious proof because there's no point, because there's a much better proof. But that much better proof we can't do either because it's a little sophisticated. So I'm just not going to prove it at all. Anyway, I'm just going to assert it. Okay. What do you think? Everybody good? All right. Okay, now in some sense I threw away some free information here. I threw away some information that you'd think should be useful for something. Namely, I had a matrix, and we computed its determinant. And then I realized that determinants have a magnitude and they have a sign, plus or minus. And I just took that sign and I just threw it away. Because we take the absolute value. That's throwing away the sign. Well, maybe that sign means something. What is that? What does the sign being plus or minus, what does that tell you? Is there something important about the sign being negative? And it turns out, yeah, absolutely. What it is, I guess I have to zoom out one spot here. The sign tells you whether your list is counterclockwise as I have it drawn here. So you can this A first, B second, A first, B second. This is counterclockwise. The sign tells you whether the list is counterclockwise as I have it drawn there versus clockwise as I, of course, could have drawn it differently. The sign decides for you. So let me, so this, by the way I have this drawn, just looking at this picture, I can immediately see, A points that way, B points this way, geometrically obvious that is counterclockwise, and therefore, even without knowing the vectors, the mere fact that I see that this is counterclockwise, that already tells me that determinant is positive because of this rule. And again, I'm not going to prove this theorem. You can just take that as a given. Okay. And the other way that it could have worked out, now let me draw the other scenario. If it had been that, that this was B and that this was A, right? Well, A first. Let's see here. B second. That list, A first, B second, is clockwise. And if that had been the picture, clockwise means the determinant's negative. Okay. All right. Again, there's a third case. The third case is where the A and B are dependent. If you think about it, this is kind of a anomalous, sort of weird case. If A and B are dependent, this becomes a very strange picture because A maybe is like that, and then B is multiple of A because they're dependent. And what is the parallelogram for which these are the edge vectors? Well, it's about like that. Not much of a parallelogram, more of a line segment, right? There's no area. There's neither clockwise nor counterclockwise. The whole thing is weird. Okay. All right. Okay, yes.
What does it mean that the plane is squished? Is it like
Yeah.
the same thing as non-existing?
Yeah, well, that's right. No, it just, what I mean by squished is, and thank you for asking, I was going to get to that, but let's do that now. So keep in mind, well, let me come back to here. Keep in mind, this parallelogram here is the image of this parallelogram, aka that square there, right? And so this, the amount of area that I have inside of there turns into, well, however much area is in there. And so altogether, as I have it drawn here anyway, it's sort of, everything's sort of been stretched out by a factor of, I don't know, about 2, something like that. Okay. So, okay, well, if instead of looking like this, if the parallelogram were, again, that vector, and then the parallelogram therefore sort of looks like that, and it's just a line segment, that means that all of this area, a positive amount of area, has been smushed down to no area, right? And so there's a kind of I think I just called it squished. Yeah, that's right, squished. Everything's been sort of squished. 2-dimensional regions are pushed down to 1-dimensional regions. Just calling it a squish. Is that cool, everybody? Okay. All right. Okay. Another thing I wanted to talk about, this business about inverting. I say here that in the negative determinant case, the plane has been inverted. You might think of that as a reflection. Let me tell you what I'm talking about here. Let's look at, again, here's E1. And let's suppose the image of E1, and again, I want to do this, I'm going to have this be B, and I'm going to have this be A. So there we go. So the image of E1, the first column, the A vector is that. Is A, and then let's see, the image of E2, here's E2. The image of E2 is like that. And I claim there's been a sort of a flipping over in the sense that the ordering here, that's counterclockwise. Blue to orange is counterclockwise. But here, blue to orange is clockwise. And I appeal to your geometric intuition. How could that be? Right? What does this linear transformation do? It looks like it rotates a little bit. And maybe it kind of stretches out this way a little bit. But however you rotate, however you stretch, there's no way you're going to get counterclockwise to turn into clockwise without flipping it over. Does that make sense? Right? Is that cool? Who asked me this? I forgot. Anyway, let me just observe in general. Counterclockwise, if you stretch it this way, still counterclockwise. If you squish it, if you shear it, still counterclockwise. The only thing that will make it anything else is to flip it over upside down. And so you might say that the plane has been flipped. You might say that it's been reflected, right? If you think about it, a flip is the same as a reflection through a line. And just as a catch-all, I'm saying inverted as being sort of any of those are all equivalent anyway. So this is just a more general term. Does that make sense to everybody? Okay. Okay, so I wrote this in 2 dimensions. Guess what? There is a 3-dimensional version of it. And what I think is beautiful about this is exactly what you would think. I mean, honestly, if I were to tell you, hey, here's the 2-dimensional theorem, just guess what you think the 3-dimensional version of this would be. Right? Well, instead of a list of 2 vectors in R2, we'd have 3 vectors in R3. Instead of talking about clockwise, counterclockwise, it'd probably be right hand, left hand. That's the 3-dimensional analog anyway. We'd have a 3x3 matrix. We'd have here, I don't know, I think I would guess, unit cube, maybe? And then we'd have a parallelepiped. I would guess volume instead of area. It would seem like the 3-dimensional analog. This is wild guesses. And yet, it's all correct, right? The at best pattern-motivated guesses that you would make work out exactly right. Right. So if you have 3 vectors in R3, then you get a 3x3 matrix, which defines a linear transformation from R3 to R3, through which the image of the unit cube is a parallelepiped whose volume is the absolute value of the determinant, and the order, here's where it's hard to draw a picture, but the order of ABC, whether ABC is right-handed or left-handed, is arbitrated by whether the sign of the determinant is positive or negative. And again, there's the anomalous, annoying case of the determinant could be 0, and if it's 0, then we don't have a parallelogram, a parallelepiped like this, right? Here's 3 vectors that are independent, and you can imagine they make a sort of a solid, a substantial parallelepiped. Now, what if I were to do this? What if the 3 vectors were dependent? Well, then my parallelepiped is flat, and it has no volume, and everything's been squished, right? In kind of the same way as we talked about before. So, yeah. So, exactly analogous. Okay. Alrighty. Okay, so we've talked about orders. We've talked about determinants. And I hope you remember all the other facts about determinants for Math 218. So now I'm going to talk about cross products. I'm going to basically just enumerate a list of properties. Again, you're not responsible for the proofs that I'll be kind of waving my hands at, sadly, because the proofs are beautiful and I love talking about them, but we just don't have time. So starting off with the definition, here's the definition of the cross product. It's a formula. I should say this is the definition I'm going to give you for the cross product. It's a formula. I will recognize that the way I'm presenting these ideas is different from the way the book does. It's very much a pro-con situation. It's very much a sort of, preference thing. And I think that the order that I present the ideas is more geometrically satisfying, but that's just my opinion. And I encourage you to take a look at the book's presentation. I think you're going to find the book's presentation is pretty heavily algebraic. And, I think that's a pretty good description. Heavy, algebraic. Anyway, I like mine. It's more geometric and picture-oriented. Okay, so anyway, here's the definition. Now, I want to recognize I have never memorized this formula, ever, in my life. Never did it. I don't trust myself to memorize it. I am sure that at some point I would get this one, for example, backwards, and I would write it down as A3B2 minus A2B3. Because it's so easy to, they look just alike, and it's be really easy to mess that up. I know I would. What I have memorized and couldn't forget if I tried because how strongly the pattern holds is this formula. And look how easy it is to memorize. You put the standard basis vectors across the top. You put the first vector on the next row. And then you put the second vector on the last row. Hey, there's not much to remember, right? And then the determinant gives you the formula for the cross product. It's fantastically convenient. So I'm a big fan. This is the one I've memorized. You better than I do. If you would prefer to do it this way, you can. Just be real careful with those minus signs. Right? It's easy to mess that up. Okay. I want to acknowledge there is something awkward about this formula. Oh, you have a question?
Is there a cross product formula for vectors in R2?
Not in R2. There is there's a generalization. I'm going to say there's a weird generalization of this in dimensions 4 and higher.
Okay.
The thing is, it's not what you call a binary product. So a binary product means there's two inputs, right? That's binary. If you're in 4 dimensions, you need to have 3 vectors to input to make a generalized cross product. And if you're in dimensions, you need n-1 vectors. And it's kind of weird. It's a great question, by the way. And FYI, y'all will see that on the homework if you haven't noticed it already. But in section 1 point, I don't remember which one, I'm sorry. Maybe it was, I've forgotten where it is. But anyway, there is a homework exercise where you'll actually work with and do a couple of basic things with the generalized cross product. Yeah. Anyway. Okay, so I want to recognize there is something awkward about this formula. I've said determinant. When you take the determinant, it's supposed to be of a matrix. When you have a matrix, aren't the elements supposed to be numbers? Right? Well, what's going on here? That's not a number. That's a whole vector. You're allowed to do that? You're allowed to stick in a vector in there? You just put anything you want in there? What about a car? Can I put a car in there? Is that a thing? No, that's what is this putting a vector in there where numbers are supposed to be? Right, highly suspicious. Okay, so absolutely fair. You're right. So this is what I'm going to call, you see I have it written here, a symbolic determinant. I acknowledge that, what I've written down here is kind of bogus. But if you just kind of don't worry about that, and if you just write out compute the determinant of this thing as if that were okay, well, then you'll get this formula. In other words, it's a very convenient abuse of notation. So anyway, don't worry about the fact that it is an abuse. It's okay. Victimless crime in this case. Okay, how are we doing? Okay. All right, so now, again, I don't want to get bogged down in the algebra and the proofs and such, but I'm going to recognize real quick that this expression here, the dot product with a cross product, if you multiply it all out, and again, cross product, here it is, there's the cross product. If you multiply this whole thing out and compare and compute blah, 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 what you find is that it's equal to that very convenient and simple little determinant. And notice, this is just beautiful how nicely this works. First vector, first row. Second vector, second row. And, running out of colors. Third vector, third row. So, wow, how about that? We already know determinants are interesting. This is a straight up perfectly legitimate, nothing scammy about this, right? Perfectly legitimate determinant that is equal to this little construction that we've written down here, seemingly no particular reason. So that means that this construction is interesting. It is literally a determinant. So this is a cool thing. And so this formula is a really useful formula. It's called the triple product formula. No surprise, this is called the triple product. And the fact that this is equal to this is extremely useful because we understand determinants. We understand dot products. And therefore, we have a formula here where we have involved the thing we want to understand, namely cross product. We've got it very closely connected to things we do understand. And ultimately, if you were to follow through the proofs that I'm going to skip over in the next 5 minutes here, then this fact factors in very heavily. Very cool fact. Okay. All right, so here we go. A bunch of properties that I'm not going to prove. If you take a cross product, then that is orthogonal to the first vector involved in the cross product, and furthermore also orthogonal to the second vector involved in that cross product. So cross products return a vector perpendicular to both of the inputs. Very cool, very useful. We're going to find situations where we have a couple of vectors and we want to find something perpendicular to both of them. Cross product does it for us. Is that cool? Okay. A couple different ways you can see this. Orthogonality, anytime you want to prove something's orthogonal, you can just take the dot product and confirm you get 0. So you could do that. You could just brute force punch it up. But there is a cool geometric way to see it as well, and I love this. This is a really elegant point of view, and you can see it involves determinants and volumes, and it's very interesting. Give it a look if you like. I think it's really neat, but you don't have to. You're absolved. You don't have to. But there's good aha moments in there if you're interested. Okay. Triple products are preserved by cycling. So again, you can take the third vector, put it in the second position. The second vector, put it in the first position. The first vector kind of falls off, and you put it back around in the original third position. And you get the same triple product either way. Very weird. After all, at a glance, A here is not involved in the cross product. But in the next expression, A is involved in the cross product. Wait a minute. How could these be related? This is a complete jumbling. It doesn't look like it ought to be related, but they're always equal. And likewise the other one. When you cycle, like I did here. Ultimately, the reason why is because triple products are determinants. Determinants relate to parallelepipeds and handedness. And cycling preserves handedness, and it doesn't change the volume, and you can kind of see that this... Anyway. Neat facts. Again, I wish I could spend time talking about the proofs. You just need to know that these are true. Okay, this next one, really surprising result. The magnitude of the cross product means something. It is the area of the parallelogram. This is a notation that I think I may have invented. I'm not sure. Maybe I subconsciously just stole it from somebody. But two parallel lines followed by a couple of vectors. This means the parallelogram defined by these two vectors. It's pretty natural. So yeah, the length of the cross product is the area of the parallelogram. So now again, weird, right? Because the cross product is defined algebraically. Here we're talking about parallelograms and areas. That's very geometric. So surprising in that sense. It's a wonderful proof. Again, I wish I had time. This is what I call a mathematical bank shot. We're trying to show that these two things are equal to each other. So rather than compute one and derive the other, or vice versa, I'm going to compute a third thing that is actually not equal to either of the objects that I'm interested in. And believe it or not, by computing this purple thing, the conclusion will be that these two green things are equal to each other. It's weird. You wouldn't think that by going that way you would get there. Thus the name bank shot. It's a pool reference, right? But anyway, again, you're not responsible for this proof, but if you're curious, I think there's a lot of good opportunities for thinking about how these things work and a couple of aha moments, and I hope you'll give it a look. But again, not responsible. Okay. Okay. If the cross product is 0, your pair is dependent. Again, you're not responsible for the proof. Take a look. It's not hard. That's appealing. But it's a good thing to know. Cross product is 0 means dependent. This list, so this is called the right-hand rule. This list where you take two vectors and then follow up with their cross product. That's, I'm going to say loosely, sloppily, apologies, right-hand order. And okay, technically it's not always right-hand order, but it is never left-hand order. And the reason we say right-hand order is because we want to call it the right-hand rule. It would be a little silly to call this the not left-hand rule. I don't think that rolls off the tongue as well. Right? So there is a possibility, of course, that one of these vectors might be 0, or a couple of them might be 0, in which case it would be neither right nor left-handed. But this list is never left-handed. Generically, it's right-handed. Also important to know. So right-hand rule. Okay, this is just a kind of a cultural observation. You'll notice if you look at our textbook that they start with a geometric definition of the cross product. They don't start with the formula. They say let's define, first cat out of the bag. Let's define the cross product to be the unique vector that has these three properties. And you're looking at that like, I'm not even clear that there is a vector that has these three properties. I'm also not clear that there's a unique. I mean, it's what a weird thing to write down, right? And then from this, they play around and actually derive the formula that we started with. Pro-con. There's some really beautiful things about doing it this way. It does end up being a little bit opaque and heavy, though. So I think you'll like my way better. But anyway, you can do it this way as well. And it's a couple of quickie observations. If you switch the order of the cross products are not like dot products. They're not commutative. If you switch the order, you get a minus sign. So cross products, they're not commutative. They are what we call anti-commutative. Anti meaning this minus sign right here. But you got to make sure to remember that minus sign. We've already talked about this, but I want to sort of say it for the record. Cross product with a given fixed vector can be thought of as a function, right? Cross product with a given fixed vector allows you to take any vector x and you can compute and then see what you get. So this is a function, and that function, cross product with a fixed vector, is linear. And we talked about this earlier this week. I think it was on Monday. And here all I do is I just write down what that explicitly means. Here's where the transformation is. Or you can go the other way if you want. You can do the cross product on the right side. And notice in both of these cases, what it boils down to, what we're saying is it boils down to saying that doing the linear combination first, followed by a linear transformation, versus doing the linear transformation first, followed by the linear combination, you get the same thing either way. So that's just linearity. Okay. And it's not associative. It's kind of like, you remember how matrix multiplication is not commutative? Cross products are not associative. And so this is a landmine. Make sure not to step on this landmine. Easy to find counterexamples where this just very clearly doesn't work. Okay. You can take a look at these applications if you like. These are not critical to math, but if you're curious, where do cross products show up in the physical world? Well, if you want to understand torque, the natural formula for writing down torque is as a cross product. And if you want to understand forces involved, magnetic fields are weird, by the way. And the way forces, you would think the forces always go in the direction of the, how for electric fields, forces are in the direction of the electric field. Not for magnetic fields. The force is always perpendicular to the magnetic field. In fact, it's a cross product. of the magnetic field and the velocity weighted by the charge. So again, weird, but cross products are how that shows up there. Okay, we're done. Sorry to go a little over there. Y'all have a great weekend. Don't forget homework. The first homework assignment is due tonight at 11 p.m. And have a great weekend. See you Monday.